Hello all. Here together we're yet to solve another electric field problem. We are going to calculate the electric fields due to a disk charge that has a total charge Q distributed across its surface, and the radius is given as R0. We're asked to calculate the electric field along the center axis of the disk at a distance x from the center. So let's again start by defining a coordinate system so we can easily define our vector components, integral limits, and so on. Placing a coordinate system at the center of the disk is a good idea so that the disk lies on the YZ plane and we have the center axis of the disk lying on our x-axis. So we had these number of steps defined to tackle a problem like this. We want to utilize the electric fields of known quantities, and we used to do that with point charges using dE as k dq over r squared in the previous problems. But that would mean that we would have to take a point charge on the surface, write the electric field at point P, and try to imagine coordinates on x, y, and z axes, try to find a symmetric one, and so on. This would be a mathematically challenging question. Well, to define a dq, we can act smart and define dq as a ring on the surface of the disk. Define a ring on the surface of the disk. This is advantageous. Why? Because in the previous problem we calculated the electric field due to a ring charge, and we can use that as our dE in this problem. So let's get started by picking out this dq. Let's say that this ring charge on the surface of the disk charge has a radius r and it has a thickness dr. This thickness is important. Why? Because dq is not a line charge anymore. We have a surface charge distribution. We have charges on the surface of the disk. So we have to use surface charge distribution sigma and define an area. So we need this dr. How do we define the area of a ring? Well, if we cut it open, it would form a rectangle. The thickness of this rectangle and the side of this rectangle, it would form a rectangle. One side of this rectangle would be 2 pi r, and the other side of the rectangle would be the thickness of this ring, dr. So we can rewrite our dq as sigma times dA, area of this rectangle, the small area of this rectangle, which is 2 pi r dr. We're not given a sigma, so we'll have to rewrite that as total charge Q distributed on the surface of the disk, which is a circle with area pi r0 squared, 2 pi r dr. Hence, pi's will cancel. We're going to be left with a dq, that is q 2q r dr over r0 squared. All right, now we have a dq defined. So we can move on to defining a dE by this dq. Well, we saw that the ring charge creates an electric field that is along its center axis, that's away from the ring charge. So here is our dE vector created by this dq. But how do we write dE? Well, we have to remember what the electric field of a ring charge was. kqx over x squared plus r squared to the power 3 over 2. But we have to redefine, so I'm doing these two steps together. We have to redefine all these distances, radii, with respect to our current definitions in the current picture. So E ring is going to become our DE. Q is going to become our DQ that we defined. X was the distance from the center of the ring to the point on the center axis. It's the same X that we have here, so we're keeping X. X squared plus R was the radius of the ring in the previous problem, and here we define it with a small r. So here we have an expression for DE. Now we can move on to defining components, but it's pretty easy in that sense because this DE has only one component, and that is along the x direction. So we have a DEX. Now we can move on to defining the limits and calculating an integral. All right, so all we need to do is integrate both sides after we define limits for this integral. What are the limits? Well, the limits are defined so that we're covering all of the charge with respect to the boundaries on our coordinate system, and we have to look at our variable. Our variable here is r. That makes sense. Why? Because I can cover the whole area of the disk by adding up small rings inside one another. Small rings inside one another. One here, another one there, another one here. Terrible. This makes sense. Why? Because we can represent the ring. This makes sense. Why? Because we can cover the whole area of the disk by adding up rings inside one another, varying the radius of the ring. We can add up infinitely many rings to cover the whole area of the disk charge. So our integration is over the radius of the ring. And that radius of the ring, we're adding up rings starting from all the way from the 0 radius all the way up to this very big ring with radius r0. So our limits go from r equals 0 to small r equals r0, the radius of the disk. So the electric field can be written as an integral of this parameter above. Let's take the constants out to see what we have inside the integral. We have two constants, k constant, q, x is a constant, over r0 squared, which is also constant. So inside the integral we have an r dr divided by x squared plus r squared to the power 3/2. All right, this integral is not bad. See, if we call this parameter inside the parentheses as u, so u is x squared plus r0 squared. Then du, we take the derivative of both sides. So du is derivative of this other side with respect to x is 2x. And then we put a dx. So du is 2. So u is x squared plus r squared. Hence, du can be defined as derivative of this side with respect to r is 2r times dr. So now let's go back to this integral and rewrite the parameters. So here we have in the integral r dr up top here. R dr is half du. Du over 2. And here we have u to the power 3/2. So this is rather easy integral. We have 1/2 as a constant, and we have du So here we have 1/2 du times u to the power minus 3 over 2. Integral of this is 1/2 u to the power minus 3 over 2 plus 1, which is minus 1/2, divided by the constant up top, minus 1/2. Giving us an integral result that is 1 over square root of u with a negative sign. All right, from here. So let's clear it out a little bit and rewrite our expression for the electric fields, which is k q x. We have a 2 over r0 squared. Now the result of the integration is minus 1 over square root of u, and for u we're going to plug this value back in. So we have minus 1 over x squared plus r squared to the power 1/2. And we'll plug in the limits from 0 to r0 for r. All right, let's do that. So the electric field is 2kq x over r0 squared in parentheses. Since there's a negative sign, I'm gonna put the lower limit first so that I multiply my limits with a negative sign. So here I'm gonna have 1 over x squared to the power 1/2 when I plug in 0 for r, which is just going to be 1 over x minus 1 over r x squared plus r0 squared to the power 1/2. There's an x in the numerator, so I'm going to put it inside the parentheses. My electric field becoming 2kq over r0 squared in parentheses 1 minus x over x squared plus r0 squared to the power 1/2. and we close the parentheses. So we have an expression for the electric field. So let's see our result here. Electric field of this discharge, hence as we calculated, is going to be along the positive x direction. This is our final vector, and the value is 2kq over r0 squared, 1 minus x over squared x squared plus r0 squared. So that's our final answer. Maybe one more detail is that note that there's q over r0 squared here. As you remember, we defined sigma as q over pi r0 squared. So what we're seeing here is that this parameter here is sigma times pi. So we can rewrite E as 2 pi k sigma 1 minus x over square root of x0 plus r0 squared. And you will notice one thing here. If you make this disk infinitely big, meaning r0 goes to infinity, this parameter here, which scales at 1 over r0, will vanish and become 0. Hence, the electric field for an infinitely big disk is going to be 2 pi k sigma, which is 2 pi. K is 1 over 4 pi epsilon 0 times sigma, and hence this 2 pi will cancel off with this 4 pi, leaving a 2 in the denominator. So we're going to have sigma over 2 epsilon 0 for the electric field due to an infinitely big disk charge. So we're actually here rederiving and redefining the electric field due to an infinitely big sheet charge. And since it's infinitely big, it doesn't matter whether it's round or square, it doesn't matter. We still get the same result of sigma over 2 epsilon 0 for infinitely big sheet charge. All right. And that's all for now for calculating the electric field of a surface charge distribution here in the shape of a disk. See you all next time.